Hello. In this video, we are going to apply our hypothesis testing methods to a numerical example about I-beams. Like I-beams are these kind of steel beams used commonly in construction, right? So the point here is the height of this I shape must be 80 millimeters. That is the standard. So as you can imagine, if it's like not in the correct size, then the safety of the construction could be in danger. So we have to make sure the I-beams are in the correct size. So we are going to use that as our example here. And we are going to apply three different hypothesis testing methods. One is the t-statistic method, and the other is the p-value method, and finally the critical value method. So we will try all these three methods and we'll conclude that those methods are actually the same. So in the end, they have to lead to the same conclusion as they should be. Let's start. Like first, we would like to test the hypothesis formulated this way. I believe that the I-beams are in the correct size, which is the average height, expected height is 80 millimeters. When you measure the height, it should be 80 millimeters. But if it's wrong, that is the alternative hypothesis, such that the expected height is not correct, right? Where I define x as a random variable for the height of a randomly chosen I-beam, right? When you randomly choose an I-beam and measure the height, the outcome is x. And mu is the expected value, the true mean of this random variable. That is our setup, okay? So, like after setting up this hypothesis, I look at the data. I collect data by randomly collecting 400 I-beams and measure their heights. And I found that the average of 400 I-beams were 79 millimeters, right? X bar, the sample average out of 400 observations was 79 millimeters, and the standard error was 10 millimeters. So here, then we have to think about this. Oh, okay, so the average is different from what I expected, but this could be just a measurement error, right? Like, so suppose that the measurement error is quite a lot, which is reflected in the standard deviation, right? So the standard deviation is 10, like, which is pretty large. That means the inspectors are not doing it carefully. So the measurement errors are pretty, there exist measurement errors, but we need to check if it's purely measurement error or the I-beams are actually in a wrong size. So first thing we have to do is to find the t-statistic. T-statistic is the standardized difference between your data and your hypothesis, right? So try to calculate based on those numbers. Okay, so pause the video whenever you need. So the data is 79 and your belief is 80. So the difference is -1, right? -1 must be standardized by the standard error. Standard error depends on the standard deviation. This is standard deviation of a single I-beam measurement, and the sample size is 400, right? Then you are going to standardize like this. Square root of 400 is 20, so the standard error is 10 over 20. So if you calculate this simple algebra, then you are going to get -2. That is the t-statistic. That means what you get is 2 standard errors below what you assumed, right? 2 standard deviations, 2 standard errors below your hypothesis. So now you have to make a decision whether this -2 is too far or close enough, right? Too far from 0. If it's close enough to 0, then your hypothesis is good enough, good, because the difference is small. However, if you believe this -2 is too far from 0, then that means your hypothesis and your data are too much different. So you have to reject your null hypothesis. To make that decision, we are going to use the significance level of 1%, right? 1% is our standard, right? Based on this significance level, find what is the rejection rule, what is the decision rule to reject the null hypothesis. Okay, first, again, pause the video if you need more time. First, in doing this, you have to think about the direction of the inequality. I said you are going to reject the null hypothesis if the data and your hypothesis are too different. So if they are close to each other, t-statistic will be close to 0, right? Then you don't need to reject your null hypothesis. When they are different, when the null hypothesis is different from the data, then the t-statistic will be different from 0, right? That means your rejection rule must be in this direction. A does not make sense. Like the absolute value of t is smaller than 1.64 means it's close to 0. If t is 0, still this inequality will be satisfied. So you cannot reject under this inequality. So A and C are automatically failure. Now you have to find a number that corresponds to the significance level of 1%, right? That means on the standard normal distribution, you have to find 2 points that makes the tail probability 1%. That is 2.58, right? You may remember. So this is 2.58. That is the threshold, the cutoff at the 1% significance level. Okay. So then, now you make the decision. Our t-statistic was -2. Our cutoff was 2.58. Does that mean we are going to reject or not? Okay, there is no algebra. It is simple comparison. You just tell which direction you are going to consider. So I said t-statistic is the difference, standardized difference between your hypothesis and the data. And if it's too large, you are going to reject the null hypothesis. And how large is it? How large is large? Too large? That is given by this number. 2.58 becomes the comparison. So as you see, -2 is close to 0, then -2.58, right? So this means if your t-statistic is within plus minus 2.58, so 2.58 plus minus 2.58 is the boundary, is the threshold. But -2 is within those interval, right? Therefore, you cannot reject the null hypothesis. -2 is closer to 0 than your cutoff. So the distance is not too large. Okay, so that is how we conclude. The answer is B here. Okay, so within the threshold. Now, let's think about this. What happens if you increase alpha to 10%? So think about it. Everything, the data are the same, but I just increased the alpha. Okay. When you change alpha, remember t-statistic does not change. T-statistic is not affected by the alpha significance level, but the thresholds are affected. So 2.58 was for 1%, so that plus minus 2.58 contains 99%. Now you have to find a new value that contains 90% between plus minus something, right? Plus that value will be smaller than 2.58. So if you go back to like a previous video, I gave you uh, the number that corresponds to 10%. That was 1.64. So if you uh, if you choose 10%, your thresholds become plus minus 1.64. Now, when you change the thresholds, the t statistic is now outside. So you are only accepting plus minus anything, something between plus minus 1.64, but minus 2 is of course like more negative than the lower end. So you are going to reject the null hypothesis now. Okay? So this is why when alpha increases, you are going to make more rejections. When you increase alpha, you are going to increase the hurdle. That means you are going to shrink the acceptance region. The acceptance interval becomes more tight. Okay, so far it was a simple numerical example based on the t statistic, right? If you make the decision based on the t statistic, you had to follow these steps and you could try like different alpha as I just showed you. Now, next, we are going to apply the p-value approach. So based on the same data, now we have like t-statistic minus 2 we already calculated. From this, try to calculate the p-value. So you will need Excel. You will need the Excel or standard normal calculator to calculate the p-value. You will need more time to pause. So pause the video. I will show you the answer. So minus 2 is the t-statistic, and on the standard normal distribution bell curve, you place minus 2 here. We are going to calculate the tail probability outside of minus 2 because those are the probability that's less likely or more suspicious under your null hypothesis. So more different from your null hypothesis. But at the same time, so we calculate tail probability outside minus 2. But at the same time, you have to think about the positive side. So on the positive side, there are equally unlikely outcomes. So you have to calculate the other side tail probability, right? So mathematically, you can write it this way. So we are going to calculate probability smaller than the negative tail plus probability greater than the positive tail, right? In this case, t is minus 2. So after taking absolute value, you get minus 2 and 2. So anyhow, you are going to calculate the probability outside plus minus 2. That is what you are going to calculate, what you need to calculate. Okay? So then you find these probabilities. This is particularly the cumulative probability you can use for the calculator. That is 2.275%. And on the other side, the other tail must have the same probability because standard normal distribution is symmetric. Normal distribution is always symmetric. So the other tail has the same probability. So the sum is the p-value, which is 4.55%. That is the p-value. Okay. So then in this case, given this p-value, now let's think about when you can reject the null hypothesis among 3 most common significance levels, right? 1%, 5%, or 10%. When can you reject the null hypothesis? So remember, what you need to remember here is you are going to reject the null hypothesis if p-value is smaller than the significance level, right? So remember, p-value is the ranking of the most suspicious, like ranking of the suspiciousness. The most suspicious is 0%. 100% is the least suspicious. And alpha, the significance level, is how much you are willing to reject, right? So for example, if you are willing to reject 10%, then you are going to reject the most suspicious 10% outcomes from 0 to 10%, okay? then 4.55 will be rejected at 10%. Right? It's included in the 10%. But if you are willing to reject only 1%, that means 4.55 is outside of the rejection. Right? You only reject top 1%. So in that sense, to reject the null hypothesis, the significance level must be greater than the p-value. So among these three candidates, 5% and 10% will reject the null hypothesis, right? Because that makes p-value smaller than the significance level. So the answer is D, David, right? So, and as you just saw, this is another illustration of why you reject more null hypothesis when you increase the significance level. When you increase alpha, then you are willing to reject more, so you will reject more, okay? So this is what I just explained. And next, now we are moving to the critical value approach. So now fix alpha at 1% and find the critical values. So you will need to check the formula in the previous slide, previous video. So if you need more time, pause the video now. I will explain. So reminder, what we are going to, the critical value starts from the center. The center is your null hypothesis. In this case, the null hypothesis is 80. You believe that an I-beam is 80 millimeters tall, right? So 80 is the center point, and you allow a certain margin around the null hypothesis value, right? So you have to calculate the null hypothesis, the margin for the critical values. That is given this way. So this is the null hypothesis. This is the null hypothesis, which is 80, pretty simple, but we need to calculate this part. This is really similar to the confidence interval, right? Z alpha over 2 is calculated from the standard normal distribution. And this part is S over square root n is the standard error of the sample average, okay? So, and you need alpha 1% to determine Z. This Z value, Z alpha over 2 value, depends on alpha. And we know that because we are using 1%, we are going to use 2.58 for this constant. This constant should be 2.58, which is given by the significance level 1%. And standard error is from the standard deviation and the sample size. So you get this simple formula, then you can calculate that. That's pretty straightforward. Okay, then after calculating those critical values, now you have to make the decision whether to reject the null hypothesis or not. So remember, our data was 79. The sample average from the data was 79. Then, given the critical values, do you reject the null hypothesis or not? Okay, so let me explain. So the critical values are designed as an interval around your null hypothesis. So you believe that the truth is 80, but because of random errors, your observation, your data may deviate from the belief, the truth, a little bit. So you allow a certain margin. That's what we just calculated, right? So you believe that the truth is 80, but because of random errors, it could be somewhere in between these two. You accept that much, right? 78.71 up to 81.29. That could happen because of measurement errors, right? However, if like, and in this case, also you allow that much, and you observed 79, which is in between those two numbers. So it's within your acceptance region, right? So you do not reject the null hypothesis. So 79 is close enough to your null hypothesis, right? like closer than the margin you allow. Given the margin you allow, it's close enough to your null hypothesis. So you do not reject the null hypothesis. So you can think it as a comparison between the null hypothesis and the data. Okay. Now another experiment. Now you change alpha to 10%. What? How would the critical values change? Try this again. Now you know the formula, so it should be much easier. You can do it. Okay, so let me show you the answer. Only this part changes, right? So for 10%, the constant from the standard normal distribution must become 1.64, right? So plug that in here, then you get another critical values, another pair of critical values, right? What you see here is, so in this place, instead of 1.64, we used 2.58 when 1%. But as you increase the alpha, the constant decreased. That means your acceptance region is now smaller. You do not allow much margin of like for your data. That means you are willing to reject, like accept less. We are willing to reject more. So alpha, you are now willing to reject 10%, which is more than the previous one, 1%, right? So your acceptance region must shrink. So it shows that higher alpha increases rejections, right? And so up to here, we tried 3 different methods: t-statistic approach, p-value approach, and critical value approach, and all 3 imply the same decision. So no matter what you do, your conclusion should be the same. And also that means you can just choose whatever you like, which is more convenient. Okay. Finally, let me try another simple experiment. Now I am changing the null hypothesis. So previously, I believed that the null hypothesis was that the I-beams are correctly sized. However, now I believe that the I-beams should be in a wrong size. So I believe that, like, for some reason, I believe that the I-beams are 2 millimeters smaller than it should be, right? So somehow I believe that the expected height is 78 millimeters, which is wrong. So under this hypothesis, I use the same data. Then try this. Then see if you can reject my new hypothesis at 1%. You may use any method you want to use, right? It's up to you. At 1%, you can calculate t-statistic or p-value or critical values and make the comparison and see if you can reject or not. Okay, so pause the video here. I will give you the answer. So if you use the t-statistic, you are going to get 2 plus 2 now, because the difference is plus 1 now, right? Your belief is 78. The data sample average is 79. After standardization, it is 2. But the threshold is 2.58. Okay? And if you calculate the p-value based on this t-statistic is 4.55. Because, we are calculating tail probability outside plus minus 2. When you calculate the critical values, now the difference is the center. The critical values must be centered around 78, the new hypothesis. Okay, so either way, so think about in the t-statistic approach, your t-statistic is within plus minus 2.58. So it's in the acceptance region. You cannot reject. And p-value is greater than 1%, the significance level, so you cannot reject. Similarly, critical values are up to 79.29, but our X bar is 79. Our X bar, our sample average is included, is smaller than the upper limit, so you cannot reject. So either way, or you cannot reject the null hypothesis. Okay, that's the same result. But what is weird is, remember, in the original null hypothesis, you could not reject at 1%. That means you conclude that I-beams are correctly sized. The null hypothesis is correct size, and you cannot reject it. So you conclude they are okay. But now, under a new hypothesis, we believe that it's wrong. The size is wrong, but you cannot reject that. That means your conclusion is that the I-beams are 2 millimeters short. That means this is pretty interesting and surprising and a weird result, because we are using the same data, but depending on what null hypothesis you use, your conclusion could be totally different, right? That's because it's unfair. You are favoring the null hypothesis by construction. That's how statistical hypothesis testing works. So you should be careful when you interpret the conclusion, right? And also another way to explain this is because when you don't reject the null hypothesis, this is not strong conclusion. It just means that there are not enough evidence to reject the null hypothesis. So even though there is no evidence that shows the null hypothesis is correct, still you accept the null hypothesis. There could be just no evidence at all. That is a weak conclusion, and that may cause this kind of confusion and kind of abuse. You may abuse it if you understand it better. Okay, thank you for watching, and the next video will be the last video of this chapter. I'm going to show you another numerical example. Okay, so see you in the next video.